So we've got, first of all, for A, we have three vectors, A, B and C. We want to determine whether these vectors are linearly dependent. So the first thing that I look at is I try and compare a couple of the vectors. So I first look at A and B, and I can see that we've got 2, 1 and 3, negative 1. Now there's really no way to get from here to here by multiplying by the same number. First of all, to get from here to here I'd have to multiply by negative, and this is not negative, so there's no way of going from here to here with a scalar multiple. So I've just said A is not dependent, A and B are not linearly dependent. That is, A and B are not parallel, because there's no way for me to multiply A to get to B or vice versa. So because I know that A and B are not parallel, I can now try and show this. So if A, B and C are linearly dependent, then we should be able to satisfy C equals, and M and N are just constants, so MA plus NB, for M and N being real constants. Okay, cool. So we're going to try and determine whether or not that's the case. I'll just get rid of that T from before. So we've determined our pair of vectors here which are independent. So these are independent. We just need to determine whether C is also independent. So I'm just going to pick this up, put it on the next page, and we can start working. Once you've done one of these, they're all very similar. Okay, so A and B, we've got C. We want to show or check C equals NA, I think MA, plus NB. So we've got C, which is 5, 6, equals some constant M times A plus some constant N times B. So our goal is to try and find, is there an M and an N that exists that satisfies this expression? Okay. Now what we're going to do here is go across with the X's and the Y's. So I'm going to just write down here that for the top line, so for the X's, I've got 5 equals, I'm just looking across the top line, 2M, remember that M multiplies in here, into both, plus 3N. Okay. The next thing I've also got for the Y's, I've got 6 equals, and the M would multiply in here again, M, and then this would be negative N. So we've got 2 expressions here, and these are your simultaneous equations. So you're going to have to solve them. There's a couple of ways you could solve these. You could do this by elimination or substitution. I'm actually going to do this by elimination. So I've got 5 equals 2M plus 3N, and then I'm actually going to take, and I'm going to call this, you can call these numbers too. So I might call this one 1 and this one 2. And I'm going to take away 2 times the second expression. So 2 times this second expression would be 12 equals 2M. And then here this would be negative 2N. So all I've done is I've multiplied this expression 2, by 2 everywhere. And then I'm going to take that expression away from the top expression, because the reason that I identify that is because if I multiply by 2 here, I can get rid of the m's. You could also multiply by 3 if you want, get rid of the n's, either way. This is elimination method. Okay, rather than substitution. So we've now got 5 minus 12, which is going to be minus 7. And then you've got 2m minus 2m, which is 0, and 3n minus minus 2, which would be plus 2, so you've got 5n. Okay. So therefore, solving for n, we've got n equals -7/5, and that is an element of the reals as required. So that's our first solution. And second, once you've got what n is, you can now substitute that back in. So I'm going to sub n back into the second equation just because I don't have to multiply by anything there. So I've got 6 equals m, take away n, okay, and because n is -7/5, you've got that. So 6 equals m plus 7/5, multiply everything by 5 to get to 30 equals 5m plus 7, okay. Take away 7 from each side, so you've got 23 equals 5m, so therefore m equals 23/5, which again is an element of the reals. And that looks like a 25. I'll just fix that up. So what you've done so far is you've said you've got 3 vectors. 2 of those vectors you could see were definitely independent because they were not scalar multiples of one another. Can that third vector c be written in terms purely of the other 2? Okay, if this is correct, this would mean linear dependence. All right, and you can see here that m and n are both real numbers. So what that means, therefore, c equals, and we'll put in our a and our m and our n. So m is 23/5 of a. So I'm just replacing the m and the n here. N was -7/5. And since c can be expressed in terms of scalar multiples of a and b, that means the set of vectors, that's a comma, so it doesn't look like a comma, the set of vectors a, b, c is not linearly independent. One of those vectors, c, depends on the other vectors to be constructed. So essentially it is linearly dependent. Okay, so that's what we're looking for. Sorry, I've put 2 L's in linearly. Okay, so that's the idea. The first thing is look at your vectors and check whether or not your vectors, pick 2, whether or not they're independent. Okay, if they are independent, then that's fine. You can then continue and try and construct the third vector from those 2 vectors that are independent. If you can straight up identify that 2 vectors are scalar multiples of each other, you can stop, because straight away those vectors are linearly dependent and your work's over. With this one we had, these 2 were independent, so then we tried to construct c from these 2 vectors, ma plus nb, and we found that we had 2 real solutions for m and n, so that was satisfied. And those vectors then do not form a linearly independent set. Now at this point you might want to stop the video and actually try the next one without me. Okay, and I'm just going to go through the same kind of method again, just following through with example B. So we'll put that one here. Okay, again looking at those vectors, I can see that, and I'll change the colour, so I'm using a different, this is B. You can see here that these 2 are definitely not a scalar multiple of one another. So A is not a scalar multiple of B, where K is some real constant. So A and B are independent. Now the question is, and I'll just write independent, indept. The question is now whether or not this vector C can be written as a combination of A and B. So is C equal to n times A plus m times b, where n and m are real numbers. Okay, so let's deal with that. We'll do that on the next page. So these are quite long just because you've got a lot of stuff going on, a lot of computations. Okay, so the first thing we're going to do here is try and write C in terms of A and B. So we've got C, and I think I did NA. So you've got C, -1, 0, 1. The only difference here is that it's more of a pain because you're now going to have 3 expressions. N times A, there's A, and M times B, there's B. You can also, expand everything out here if you want to see all the workings. So this would be 3n, 4n, and -n. And then 2m, m, and 3m. We're just expanding the m through. So we've got 3 expressions for x, y, and z. This is a 3-dimensional vector. So we've got, reading across the top line, -1 equals 3n plus 2m. You've also got 0 equals 4n plus m, and 1 equals -n plus 3m. Okay, so you've got 3 expressions. You've only got 2 unknowns, so actually you won't need all of these expressions to help you find n and m, but your n and m need to satisfy all of these. So I'm just going to label them 1, 2, 3 again. So I can see there for the second expression I could solve 2 for m, and then I could use substitution method. So I've got m equals -4n from 2. That's just been solved for m. And what we're going to do then is sub into either one really, it doesn't matter. I'll sub into the first one, into 1. So we're going to have -1 equals 3n plus 2 times m, which is -4n. -1 equals 3n minus 8n. -1 equals, this is -5n. So therefore n equals 1/5. And that is an element of the reals as required. Okay, so we've got n. We can now go to the next expression. I'm just going to copy this over. So I can keep working. Okay, so we've got our next expression is going to be, we can find m. So we're going to use, I'm just going to use 2 to find m, because I've got n now. So we've got 0 equals 4 times n plus m, which means that 4/5, 0 equals 4/5 plus m, and therefore m equals -4/5, which is an element of the reals. So we've got m and n now, and we just need to check that the m and n satisfy all 3 equations. Now, when we first did our substitution, I substituted 2 into 1. So these solutions here for m and n will satisfy 1 and 2, but you can check. So I'll do the checking, we'll do the checking in red. So for 1, we'll chuck in the m and the n, so we've got -1 equals 3 times 1/5 plus 2 times -4/5. -1 equals, that's 3/5, and this would be -8/5, which equals -5/5, which equals -1, so that's fine. The second expression, let's substitute m and n into the second expression. So 0 equals 4 times n, which is 1/5, plus m, which is -4/5. And you can see straight away that you've got 4/5 minus 4/5, which is 0, so that's fine. Now the only other one that we need to check is this expression here, okay, for m and n. So I'll just do that on the next page. You can see this took up quite a long. Okay, so we've got m and n. So we've now got n was 1/5, m is -4/5. So 1 equals -1/5 and 3 times 4/5. And we've got -1/5 plus 12/5, which is here, you can see this is going to be 11/5, which does not equal 1. So this last solution, or this last equation, expression 3, or equation 3 I should say, is not satisfied. And as a result of that, that means that the m and the n here, even though they satisfy the first two equations, they don't work for the third. So there exists no m and n that satisfies all three. There is no m and n which satisfies our original question, which was C equals Na plus Mb. Therefore, because there is no solution to that expression, those vectors A, B, and C are a set of linearly independent vectors, because they can't be written independent vectors. They can't be written as a combination of each other. They can't be written as a linearly or a linear combination. Linear, by the way, just means you've got linear just means that you've got those things added together in some combination. So because we found no solutions there that work for all three equations, this expression cannot be satisfied. There is no solution, and hence those vectors A, B, and C are not dependent, they are independent. So you've got a situation where you've got three vectors, none of which are parallel to each other. And that's going to be very useful later on when we start looking at proofs, and also when we get into our mechanics and dynamics. So the key thing here for linear dependence and independence, can the vectors be written if you have two vectors as a scalar multiple of one another, or with three vectors, can they be written as some combination in terms of two vectors that you find to be independent? Can that third vector be written in terms of those other two?